Modern atomic theory. An element is described as a pure substance that cannot be broken down into simpler substances by chemical means. This is given as an empirical definition, which is a statement that defines an object or process in terms of observable properties. It can also be defined as a substance composed of one kind of atom. This is a theoretical definition, which is a statement based on ideas created to explain observations. An atom is the smallest particle of an element that has all the properties of that element, which is a theoretical definition. The law of conservation of mass. This law states that matter can neither be created or destroyed during a chemical reaction, but only changed to a different form. The law of constant composition. This law states that compounds will always have the same percentage composition by mass. The atomic number is the number of protons present in the nucleus of an atom of a given element. The mass number is the sum of the protons and the neutrons in the nucleus of an atom. We can use symbolism to represent an individual atom of an element. X would be the name of the element, A is the mass number, and Z is the atomic number. Isotopes. In previous slides, we discovered that atoms of an element have the same number of protons and neutrons. However, there may be several isotopes of that same element that differ from each other only in the number of neutrons in their nuclei. This is a theoretical definition. We can use a machine called a mass spectrometer to study the structure of elements and compounds. One application of a mass spectrometer is to determine precisely the mass and the abundance of isotopes. Radioisotopes. Many elements have one or more isotopes that are unstable. Atoms of unstable isotopes decay, emitting radiation as their nucleus changes. Isotopes that can decay in this way are called radioisotopes and are said to be radioactive. So we can define radioactive as the capability of spontaneously emitting radiation in the form of particles and/or gamma rays. The half-life is a measure of the time it takes for 1/2 the nuclei in a radioactive sample to decay. For example, carbon-14 dating. This is a technique that scientists use that makes use of radioactive carbon-14 to identify the date of death of a once living material. Nuclear fission. An atom of uranium U-235 undergoes nuclear fission when a slow neutron collides with its nucleus, resulting in the formation of two lighter nuclei. This reaction also produces more neutrons and releases a considerable amount of energy. When new neutrons are released, they are traveling too quickly to cause further fission reactions. However, to be useful in continuing this chain reaction, they must be slowed down. This is achieved with the use of a moderator. CANDU reactors use heavy water, which is water that contains deuterium instead of hydrogen, to cool the fuel bundles in the CANDU reactor. This hot, heavy water is used to heat ordinary water, producing steam. This steam is then used to turn the turbines connected to electric generators to generate electricity. To learn more, read pages 34 to 35 in your textbook. To understand this in more detail, we're going to explore Niels Bohr's atomic theory. Electrons within an atom can possess only certain discrete energies called energy levels. Each energy level is a fixed distance from the nucleus, later proven to be not entirely accurate. An electron with a particular energy level travels along a three-dimensional pathway called a shell or an orbit. Quantum mechanics, then, is a new theory, relatively speaking, of the atom in which electrons are described in terms of their energies and probability patterns. Quantum mechanics describes the electrons within atoms in terms of their energy and what is termed probability patterns. The probability of finding an electron of a specified energy within a specific region of space around the nucleus called the electron cloud. You can see in this illustration the difference between the Bohr model and the quantum mechanical model. The principal quantum number is a number that specifies the theoretical energy level of an electron in an atom. This is represented by the letter N. Then we have subshells. Each orbit or shell is divided into subshells as the principal quantum number increases. So in energy level 1, N is 1, and it's the K. N is 2 is represented by L. N is 3 represented by M, and N is 4 represented by N. So valence electrons are those electrons then that occupy the highest shell of an atom that are used by the atom to form chemical bonds. This is a theoretical definition. Now let's take a closer look at the quantum mechanical theory. This formula, 2n squared, can be used to determine the maximum principal quantum numbers of a shell. N will represent the principal quantum number. The electrons in the highest occupied energy level are called, remember, the valence electrons. So if we're in energy level 1, 2 times 1 squared is 2. We will find 2 electrons in the first row. Energy level 2. 2 times 2 squared is 8. The second level. 3. 2 times 3 squared is 18, and so on. So we can have this in an easy-to-use table. So N is 1, we use the symbol K. The number of subshells is 1. The maximum number of electrons per shell is 2. Then we can move to N is 2. Symbol L, number of subshells 2. Maximum number of electrons per shell is 8. 2 plus 6. 3 is M. There are 18 electrons, 2 plus 6 plus 10. And then 4 is N, 32, and so on. This can continue. As you know, we have more than 4 rows in our periodic table. So this table summarizes the quantum mechanical theory that assigns letters for the first 4 shells. This table goes into more detail about the position and shape of the electrons in each shell, which will further explain the total number of electrons in each orbital, including sublevel shapes and spins. But don't worry, we'll cover this in grade 12. Coming up next, trends in the periodic table.